Hello everyone, and welcome back. Today we're going to continue our exploration of single variable calculus and review some of the important integration rules and methods that we have discussed in the previous videos. So let's start off with a very easy example that just uses just some basic rules and the power rule for integration. And in particular, it's an indefinite integral because there's no bounds on our integrals, which means there's going to be a plus c at the end because the derivative of any constant would be 0, and we don't know exactly if that constant was there to begin with. So for powers, except for minus 1, we're just going to be adding 1 to that exponent and dividing by that new exponent. So the antiderivative of x to the minus 3 is going to be equal to minus 3 minus 1, that's going to be equal to minus 2 divided by minus 2. And then x to the minus 2 is going to turn into x to the minus 1 over minus 1. The antiderivative of x to the minus 1, which is the same as 1 over x, is the natural log of the absolute value of x. The antiderivative of 1 is going to be x. And then here, that's the same as x to the 1 half. So add 1 to that exponent, which is going to be 3 halves, divided by 3 halves, and then the antiderivative of sine is going to be minus cosine. So we're going to have 5 times minus cosine of x plus some arbitrary constant c, and we can of course clean up this expression a little bit and write this as minus 1 half x to the minus 2 minus x to the minus 1 plus the natural log of the absolute value of x plus 2/3 x to the 3 halves, 3 halves, not 2/3. And then we're going to have minus 5 cosine of x plus our arbitrary constant c, and that is our antiderivative, right? So quite easy and straightforward. Now let's look at the antiderivative, or the integral, of secant x tangent of x plus cosecant of x cotangent of x plus tangent of x plus cotangent of x. This is also quite easy if you know your basic antiderivative rules for trig functions. So we know the derivative of secant is secant tangent, so this is just going to be equal to secant x. The derivative of cosecant is negative cosecant cotangent, so that's going to anti-differentiate to minus cosecant of x. Now, the integral of tangent is equal to what? Because, well, the derivative of tangent is secant squared, the derivative of secant is secant tangent. The derivative of a basic trig function is not tangent. But if we write tangent of x as sine of x over cosine of x, what we have here is in some sense the derivative of the natural log of cosine, because the derivative of natural log of cosine is going to be equal to 1 over cosine of x times the derivative of cosine is going to be minus sine of x. So that actually gives us a reasonable thought for the derivative of tangent. So that's actually going to be equal to minus the natural log of the absolute value of cosine. And then for the other one, well, what is that going to be? Well, cotangent is going to be equal to cosine of x over sine of x, so a reasonable guess is going to be equal to the natural log of the absolute value of sine, which is going to differentiate to sine of x on the bottom, and the derivative of cosine is going to be cosine, which is precisely equal to cotangent, so that's going to be equal to the natural log of the absolute value of sine of x, and don't forget your lovely little constant at the very end. So that's going to be our antiderivative of that original function. Right, so those were the easy ones, which just required us to know some basic rules of antiderivatives. Now let's get into substitution, which is also very common. Let's do the indefinite integral of dx divided by the square root of x, and then 1 minus the square root of x to the power of 3. So here, notice that we have an interior function that's being cubed, and derivative of square root is a 1 over square root function, which is in some sense hanging out here. So letting u be equal to 1 minus the square root of x is a reasonable guess for a substitution here. So the derivative of u is going to be equal to 1 minus 1 over 2 square root of x times a d of x, and then our differential of x is just going to be equal to minus 2 square root of x du. So when I substitute that, we're going to have the indefinite integral of minus 2 square root of x du. That replaced our dx. We're going to have our square root of x in front. Our u is what was inside of our parentheses, and don't forget your 3. So This is a good substitution, provided that everything with x disappears and you're only left with a function of u, which we have, which is a very good thing. So that means this is going to be equal to, we can factor out that minus 2, so we're going to have minus 2 times the integral of u to the minus 3 du, and then we can just use our power rule here. So we're going to have minus 2 times, so add 1 to that exponent, so we're going to have minus 2, all divided by minus 2. And then, don't forget our plus c. So notice that our minus 2's are going to cancel here, and then we're just going to be left with u to the minus 2 plus c. We did not originally start with a u function, we had an x function, so we need to bring that back into our x world. Keep in mind our u was 1 minus the square root of x, so once you bring that back, that is going to be your answer for your integral, right? So that's actually pretty nice. Now, things can get a little messy when we're working with definite integrals, where we have, for example, elements on the upper and lower bounds of our integral. Let's assume we have 5x differential of x divided by 8 plus 7x squared. So, what do we have going on here? So, we have a quadratic function in the bottom, and we have a linear function on top. So again, a u substitution probably is going to be a reasonable choice for approach here. So let's u be equal to 8 plus 7x squared, that's our quadratic, and the differential of this quadratic is going to be equal to 14x times the differential of x, which means our differential of x can be rewritten as the differential of u divided by 14x. Right, so that's our differential of x replacement, and hopefully that's going to kill off everything in our x. Now, remember, we're working with a definite integral here, which means we need to change our bounds. So when x is equal to 0 to 1, what is u equal to? So when x is equal to 0, that term is going to disappear, and we're going to be left with 0 plus 8, which is equal to 8. And when x is equal to 1, we're going to have 1 squared, which is 1. And 1 times 7 is 7, and 7 plus 8 is 15. So our new bounds for our integral is going to be 8 to 15 in that order. So we're going to have the integral from 8 to 15 of, and we're going to have 5x times the differential of x, which is du all over 4x. Let's actually write it as du over 14x, and then all over 8 plus 7x squared, which was going to be our u. So notice that our x's do eliminate, and we have a constant of 5/14 in front, so we can factor that out. So we're going to have 5/14 times the integral from 8 to 15 of du over u, which is the natural log function. So that's going to be equal to 5/14 times the natural log of u, and we need to evaluate this as u goes to 15 and as u goes to 8. So once we have that, we're going to have 5/14 times, then we're going to have the natural log of 15 minus the natural log of 8, and then we can just simplify this using our rules for logarithms, and write that as 5/14 times the natural log of 15 divided by 8, and that's probably the nicest way you can write the exact answer for this particular definite integral. The next example is actually based heavily on some basic tricks we learned back in algebra and pre-calculus, in particular completing the square. Let's assume that we have the integral of the differential of x divided by some quadratic function. So if you notice this, you're like, okay, well, x squared plus 2x plus 4 doesn't factor, so I can't use partial fraction decompositions on this unless I factor over the complex plane, but even that can be a little messy to work with. So what I can do is I can somehow transform this into, for example, an integral of 1 over 1 plus something squared with respect to u, because I know that that's going to be equal to the arctangent of u plus c. So if I can complete the square on this in some sense, then I can transform this integral into an arctangent integral, which I can easily deal with. So the first thing I need to do is analyze this x squared plus 2x plus 1. So I have x squared plus 2x plus 4. So how do you complete the square? So I'm going to take this number and I'm going to subtract or take that number, divide it by 2, and square it. So when I do that, I'm going to have a magic number of 2 divided by 2, the quantity, squared. So I'm going to have 1. So I'm going to have x squared plus 2x, and then I'm going to have plus 1 minus 1 and plus 4. So I'm just introducing this plus 1 minus 1 here, but what I'm going to do is group these first two terms. So when I do that, I'm going to have x plus 1, the quantity squared, plus 4 minus 1, which is going to be equal to 3. So when I have done this, our integral, which I'm just going to call star, is going to be now the integral of dx all over x plus 1 squared plus 3. Right? Which is a little bit more nicer to look at. At least it's sort of like the u squared plus 1, but we have this plus 3, which is actually quite annoying. So keep in mind that the square root of 3 squared is equal to 3, so I can actually write our integral as the integral of dx all over x plus 1 squared plus the square root of 3 squared. Now what I want to do is I want to factor out that square root of 3 squared out of the denominator. So when I do that, I'm going to have 1 over the square root of 3 squared, which is 3, times the integral of dx over x plus 1 over the square root of 3 squared plus 1. Right? And you can work out that algebra just in case you're not comfortable with that. And now our u substitution is very obvious. So I'm just going to be letting u be equal to the x plus 1 divided by the square root of 3, whose differential is just going to be equal to 1 over the square root of 3 dx. Meaning dx is just going to be equal to the square root of 3 times du. We don't have any bounds, so we don't have to transform them. Therefore, our integral is just going to be equal to 1 over 3 times the integral. Dx is now the square root of 3 du, and on the bottom we have u squared plus 1, which is exactly what we want. So we have that our integral is equal to the square root of 3 over 3 times the integral of u squared plus 1, which we know to be equal to the square root of 3 over 3, times the arctangent of u plus some arbitrary constant c, and then we can replace our u back, and we're going to have the square root of 3 over 3 times the arctangent of x plus 1 over the square root of 3 plus c. And that is the integral that we want. Now, there is other problems where this problem actually becomes a subset. I'm not going to call this problem 6, but I'm just going to call this like problem 5 plus, right? And that's the integral of 7x squared minus 3x plus 26 all divided by x cubed minus 8 dx. Now, if you were to see this, you're like, well, that's actually a big step up. So how would I tackle that? So the first thing that you would have to notice here is that x cubed minus 8 is a difference of perfect cubes. In particular, x cubed minus 8, we should know factors into x minus 2 times x squared plus 2x plus 4. And in case you don't remember these signs, these two signs always match, and these two signs are opposite, right? And this number 2 is the number that cubed gives you 8, and that's just going to be 2 squared, in case you're not familiar with the difference of cubes relationship. So this new integral can be rewritten as the integral of 7x squared minus 3x plus 26, all divided by the factored representation x minus 2 times x squared plus 2x plus 4 dx. And you might be adventurous and be like, well, can I factor that x squared plus 2x plus 4? You may remember that the quadratic in the difference of cubes, provided that this is a natural number, does not factor over the set of integers. Actually, it doesn't even factor over the set of real numbers. You would have to introduce complex numbers to do that, right? So you shouldn't bother trying to factor that x squared term, right? Which means, since we have a factored rational function, partial fraction decompositions is definitely an ideal approach for this particular problem. That is, I'm going to factor this into some constant divided by that linear term, plus some linear term over that quadratic factor, x squared plus 2x plus 4, dx. So we already know what a divided by x minus 2 integrates into. That's just the natural log of x minus 2. And this we can break apart into 2 or just treat it as 1 and use that result that we just had for that x squared plus 2x plus 4 denominator because that's practically what c over that term integrates to. And the bx over that term actually isn't too bad itself. So I invite you to try that on your own. But the question that I want to at least finish here is, how do you find these constants a, b, and c to substitute back? So, in order to do partial fraction decomposition, so we know that this should decompose into 7x squared minus 3x plus 26 all over x cubed minus 8. And we want to decompose this into a over x minus 2 plus bx over c over x squared plus 2x plus 4. Lots of n2's here because we have lots of 2's floating around, right? Into 2. All right, so what I want to do is multiply both sides by x cubed minus 8, and that's going to give us 7x squared minus 3x plus 26 is equal to a times x squared plus 2x plus 4 plus bx plus c times x minus 2 when we cancel out those common factors. So now we need to figure out what a, b, and c are. So we have one equation, 3 unknowns. So if we set x to be equal to 2, we can eliminate that last term there. So when x is equal to 2, 7x squared minus 3x plus 26, that's going to come out to 48. And that's going to be equal to a times, so 2 squared plus 2 times 2 plus 4, that's going to be equal to 12, and then we're going to have that plus 0 term at the end. So we have 48 is equal to 12a, which means that a is just equal to 4. So we have the first constant. So once we have that constant there, then we can actually plug that back into this case and have 4, and then expand that out, and then subtract that to the left-hand side and simplify that quadratic. So once we have that, we're going to have 7x squared minus 3x plus 26 is equal to 4x squared plus 8x plus 16 plus, then we have this thing here which we'll deal with in a moment. So what I want to do is bring that to the left-hand side, and that's going to give us 3x squared minus 11x plus 10 is equal to bx plus c times x minus 2. So now we have one equation, 2 unknowns. So the best way to approach this is to create a 2x2 systems of equations. Here you're going to choose any 2 values of x except for 0. Some good choices probably are going to be x is equal to 3 because 3 minus 2 is 1, and x is equal to 1 because 1 minus 2 is negative 1. It gives us nice numbers to work with. So when we plug in 3, 3 times 3 squared minus 11 times 3 plus 10, that's going to come out to 4. And that's going to be equal to, so we're going to have bx, which is the same as 3b, plus c, and all of that's multiplied by 1, so I don't need to change anything. And then when I plug in x is equal to 1, we have 3 times 1 squared minus 11 times 1 plus 10. That's going to come out to 2. And that's going to be equal to, so 1 minus 2 is negative 1, so we're going to have minus b minus c. So now we have this 2x2 systems of equations. We can use Gaussian elimination very easily because our c's will eliminate. So we're going to have 6 is equal to 2b plus 0, which means that b is going to be equal to 3. And if b is equal to 3, then 2 is equal to minus 3 minus c, which means 5 is equal to minus c, implying that c is equal to minus 5. So that gives us all of our constants. So that means our original integral for this extended problem, which originated as 7x squared minus 3x plus 26 all over x cubed minus 8 dx, can now be solved as this new integral, 4 divided by x minus 2, plus 3x minus 5, all over x squared plus 2x plus 4, and then we can use our typical integration tricks to take care of that term and that term, which I leave for you. Since that last example was a little bit more difficult, let's bring things back just a tad bit in terms of difficulty. Let's assume that we have an integral of a function where the top and bottom just differ by a constant, and in particular the constant is on the bottom. When you have functions of this type, it's actually very easy to solve. All you need to do is add and subtract that constant to the top, so pretty much you have the same thing on the top and bottom, plus some other stuff. In particular, what I want to do is I want to say, okay, 1 plus x squared minus 1, that's not a 1, that's an x, minus 1, all over 1 plus x squared dx. So all I've done is just introduce that 1 minus 1, which is 0, so I haven't really changed anything. Now what I want to do is I want to break this fraction up into two separate fractions. I'm going to write this as the integral of 1 plus x squared over 1 plus x squared, and then minus 1 over 1 plus x squared dx. Right? So now I have the integral of 1 minus 1 over 1 plus x squared dx, which is very easy to solve. The integral of 1 is just going to be equal to x. The integral of 1 over 1 plus x squared, that's going to be equal to the arc tangent of x plus some arbitrary constant c, and that is our answer. Very nice, actually. So now that we've made a little easy example, let's make things a little bit more fun and exciting. So example number 7, let's assume that we have the integral from 0, let's go to infinity, of x squared e to the minus x dx. Alright, now there are a couple ways you could go about this. The first obvious way possibly would be to use Laplace transform, maybe if you know Laplace transform, but if not, that's okay. Also, if you recognize this is the gamma function, because this is also the integral from 0 to infinity of x to the 3 minus 1 e to the minus x dx, which is precisely gamma of 3, because if you know what gamma 3 is, well, gamma 3 is just 2 factorial, which is equal to 2, and then we'd be done. But if you don't know how to do that, then what other tools do you have? Well, integration by parts is actually the more elementary way to approach this, right? Because if we differentiate x squared enough times, it's going to disappear into a constant, and the integral of exponentials are just exponentials, so they're actually very easy to deal with. So let's do integration by parts to illustrate this particular example, although we do know that the answer to this should be equal to 2, only if you know gamma functions, right? Let's pretend we don't. So how does integration by parts work? So we're going to let u be equal to our x squared and dv be everything else. So if u is equal to x squared, dv is going to be equal to e to the minus x dx, right? So we're going to differentiate in this direction and integrate in this direction. So the derivative of u will be equal to 2x dx, and v is going to be equal to minus e to the minus x, right? So the integral of u dv, in case you don't remember, is uv minus the integral of v du. So that's the integration by parts formula. Let's call our integral star. So star is going to be equal to uv. So uv, and keep in mind we need to apply our limits, minus the integral of v, let's change that minus to a plus, minus v du. Okay, so that's what we have here so far. So as x goes to infinity, that's going to go to 0, and as x goes to 0, that's going to go to 0. So we have 0 minus 0, which is 0, which is pretty nice. So we're going to have star is equal to, and then we're going to have 2 times the integral from 0 to infinity of e to the minus x times x dx. So notice that this is similar to the first integral we had, but now instead of x squared, we have x. So that's going to be my u. So u is going to be equal to x, and dv is going to be equal to everything else. So e to the minus x dx. So we're going to differentiate in that direction. So du is going to be equal to 1 dx, and then we're going to integrate in that direction. So v is equal to minus e to the minus x. So therefore, our integral is going to be equal to 2 times, so uv, x goes to infinity, x goes to 0, minus the integral of v, let's change our minus to a plus, minus e to the minus x du. Okay, that's great. So once we have this, what do we have? So as x goes to infinity, that exponential goes to 0. As x goes to 0, that linear term goes to 0. So this entire term goes to 0, which is great. So now we're going to have, our integral is going to be equal to 2 times this integral from 0 to infinity of e to the minus x dx, which is very simple. So now we can just use the fundamental theorem of calculus. So this is going to be 2 times minus e to the minus x, and then we're going to evaluate this as x goes to infinity and as x goes to 0. So we're going to have minus 2 times as x goes to infinity, that goes to 0, and as x goes to 0, that goes to 1. So we have minus 2 times minus 1, which is just going to be equal to 2, which is the answer that we originally established for this problem. The next integral we're going to explore also is going to be using some factoring and some partial fraction decomposition and a couple other fundamental theorem of calculus tricks that we've already discussed up to this point. So the first thing you need to observe is that the top is a difference of cubes and the bottom is a difference of squares. Right? So if we call this integral, for example, star, since we're going to be doing a lot of manipulations to it, this is going to be equal to the integral from 0 to 1. So we're going to have x minus 1 times x squared, change the sign, plus 1 times x, which is x, plus 1 squared, which is going to be 1, all over, then we're going to have 1 minus x squared, and then 1 plus x squared dx. Then I'm going to factor this expression because that's also a difference of squares. That's going to be a sum of squares, but that only factors over the complex numbers, which we don't want to do. So therefore, our integral is going to be equal to the integral from 0 to 1 of x minus 1 times x squared plus x plus 1 all over 1 minus x, 1 plus x, 1 plus x squared dx. Right? So notice that we have an x minus 1 and a 1 minus x, which cancels in the inverse fashion because they're just opposites of each other. So I'm just going to pull that minus 1 out, and that minus 1 I'm going to reverse my limits of integration so I don't forget that minus by mistake. So then we're going to have the integral from 1 to 0 of x squared plus x plus 1 on top, x plus 1 times x squared plus 1 on bottom. Right? So now that we're in this form, now our goal is to say, okay, maybe we can use partial fraction decomposition and write this as the integral from 1 to 0 of some constant all over x plus 1 plus some linear function divided by x squared plus 1. Right? And that is going to be our desired form. Right? So one can find that through this partial fraction decomposition that a, b, and c are actually all equal to 1/2, which is actually very, very nice. So that means our integral is just going to be equal to 1/2 times the integral from 1 to 0 of 1 all over x plus 1 plus x plus 1 all over x squared plus 1 dx. So this 1 over x plus 1 term that we have here is actually pretty easy to integrate. You probably already know what it is. So that's going to come out to 1/2, and then we're going to have the natural log of x plus 1. And then this next term is that same completing the square, use substitution potentially, natural log type of thing that we talked about in the last couple examples. Right? So that's going to integrate, and again, I leave this to you as an exercise, is just going to come out to 1/2 times the natural log of x squared plus 1, and then the arctangent of x, and then plus c, but keep in mind, we're going to be evaluating this as x goes to 0 and as x goes to 1 in that order. Right? So as x goes to 0, what do we have? So we're going to have 1/2 times, so we're going to have the natural log of 0 plus 1, which is going to be 1, plus 1/2 times the natural log of 0 squared is 0, plus 1 is 1, and then we're going to have the arctangent of 0 minus the natural log of 1 plus 1, which is going to be 2, plus 1/2 times the natural log of 1 squared is 1, plus 1 is 2, and then we're going to have the arctangent of 1 there, arctangent of 1. Right? So that's going to be our expression. So the natural log of 1, that's going to be 0, natural log of 1 is going to be 0, and arctangent of 0 is going to be 0. So that entire term disappears, which is actually very, very nice. And then what are we going to be left with? So we're going to be left with star, our integral that we started with, is going to be equal to 1/2 times, let's make it a negative 1/2, because we have that negative sign there. And then we have 1 natural log of 2 plus 1/2 natural log of 2, so that's going to be equal to 3/2 natural log of 2. And then the arctangent of 1, that's going to be pi divided by 2. Right? So once we FOIL that minus 1/2, and if you so choose to, we're going to have that our original integral is just going to be equal to minus 3/4 natural log of 2 minus pi over 4. And that's going to be the value of the integral that we started with, which is actually pretty interesting. The last couple examples that I want to do involve what is called the principal value of integrals, which is often useful in, say, higher level integration methods, and also how you can use Taylor series to evaluate or approximate definite integrals as well. So what we have here is the integral of 1 over x from minus 5 to 7. So if you know anything about the function 1 over x, it has a infinite discontinuity at x is equal to 0. So when we integrate from minus 5, which is located over here, all the way to 7, we have to jump across this vertical discontinuity, right? But in some sense, this function is an odd function in terms of symmetry because it is symmetric about the origin. So the integral from minus 5 to 0 and the integral from 0 to 5 in some sense are equal but opposite infinities, right? But typically speaking, you cannot take the Riemann integral of this function, so a lot of people will just say that this integral diverges, and they would be correct. But if we were to allow these infinities of equal size to cancel, what would this integral then be equal to? So that particular problem is called the principal value integral, which we denote as PV minus 5 to 7 of 1 over x dx. Now this integral will converge because we're looking at, in some sense, the principal value of what this integral should be if we're allowed to cancel those infinities. So what we're going to do is we're going to partition this integral around that singularity of 0, which in this case is 0 itself. So that's just going to be the integral from minus 5 to 0 plus the integral from 0 to 7 of our function 1 over x dx, right? And what we're going to do is instead of going exactly to 0, we're going to approach it as some number gets close to 0, both from the left and from the right. So we're going to rewrite this integral as the limit as some number, let's call it m, as m goes to 0, both from the left and from the right. So we're going to have minus 5 to m, so that's a left-hand limit, and then we're going to have plus the integral from m to 7, so that's going to be a right-hand limit of our function 1 over x dx. Right? Now this integral, if we just sort of ignore that limit part, actually has a very nice answer because we can write that as instead as what? So this is going to be the limit as m approaches 0. Let's write this in a more formal way. As m approaches 0 from the left of minus 5 to m of 1 over x dx, and then plus the limit as m approaches 0 from the right-hand side of the integral from m to 7 of 1 over x dx, right? So this would probably be the more formal way of writing those things I was writing. So we know the antiderivative of 1 over x, and 0 is not between minus 5 and m because we're approaching 0 from the left-hand side. Therefore, this integral is just going to be equal to the limit as m approaches 0 from the left of the natural log of x as we evaluate x approaches m as x approaches minus 5. And then we have the limit as m approaches 0 from the right-hand side of the natural log of x as x approaches 7 and as x approaches m. So this is going to be equal to what? So this is going to be equal to the limit as m approaches 0 from the left of the natural log of m minus the natural log of the absolute value of minus 5. And then we're going to have plus the limit as m approaches 0 from the right-hand side of the natural log of the absolute value of 7, which is 7, minus the natural log of the absolute value of m. Then we can take the limit as m goes to 0, both from the left and from the right. Let's assume that that limit does exist, and we're just going to be left with the natural log of m minus the natural log of 5 plus the natural log of 7 minus the natural log of m. And notice that before we take these limits, these natural log of m's do cancel. So therefore that limit as m goes to 0 is irrelevant, and this is just equal to the natural log of 7 minus the natural log of 5, which from our original picture, because remember we have minus 5, 5, and 7, let's draw some non-zero area there. This is just this piece here, the natural log of 7 minus the natural log of 5, because this positive infinity and this negative infinity are equal size infinities, just opposites, so they cancel. So that's just going to be equal to the natural log of 7/5, which is going to be the principal value of the integral from minus 5 to 7 of 1 over x dx, which is not to be confused with the definite integral from minus 5 to 7 of 1 over x, which diverges. The last integral that I want to introduce to you today definitely has, again, quite a few different approaches that you could use this for. This integral is actually quite famous, and that's the integral from 0 to infinity of sine x over x. The reason this integral starts to pose a bit of difficulty is because sine x over x does not have an elementary primitive. That is, there does not exist a elementary function that can be represented as polynomials, trig functions, exponentials, at least a finite series of them, whose derivative is equal to the sine of x over x. So we can't just use the fundamental theorem of calculus in order to get this answer. Right, but if you do know any special functions, in particular the sine integral function, which is defined to be equal to the integral from 0 to x of sine of t over t, and if you know anything special about this particular integral, then you can be like, okay, well, I can be like, okay, so star is just going to be equal to the sine integral of x evaluated as x goes to infinity and as x goes to 0 and subtract, and that's just going to be equal to the sine integral at infinity minus the sine integral of 0, and if you know anything about this particular function defined here, that's just going to be pi over 2 minus 0, which is pi over 2, and then you're done. Right, and that's pretty magical, I guess, but that requires you to know a couple special integral defined functions, which you may or may not know. So another way we could do this would be like, okay, well, sine x, I know practically everything about it. In particular, it's Taylor series. So if you know Taylor series, then this solution method is going to be your favor. You could also use Laplace transforms if you're familiar with that, but maybe you don't. So let's just go with the infinite series approach. Right? So let's assume that we have this function 0 to infinity sine x over x and dx. So if you know this Taylor series for sine, then you should know that sine of x is going to be equal to the, let's write it in expanded form, in particular x minus x cubed over 3 factorial plus x5 over 5 factorial minus plus and so on. So what I'm going to do is I'm going to divide everything by x, because I'm trying to build a Taylor series for that particular function. And keep in mind, as x gets close to 0, that gets close to 1. So in some sense, sine x over x does not have a singularity at 0. So dividing by x is actually perfectly okay here, at least as long as you define that we're approaching 0 from the right-hand side and we're not exactly at 0. So once we have that, we're going to have sine of x over x is equal to 1 minus x squared over 3 factorial plus x4 over 5 factorial minus x6 over 7 factorial plus minus and so on. Once I have this, then I want to integrate this term by term. So once I have that, then I'm going to evaluate that particular series. So star is going to be equal to the integral of that particular series. So the integral of 1 is going to be x. The integral of x squared is going to be equal to x cubed over 3 factorial, which is just going to be equal to x3 over 3 factorial times 3. And then we're going to have x to the 5 over 5 factorial times 5 minus x7 over 7 factorial times 7 plus minus and so on. And then we're going to evaluate that as x goes to infinity and as x goes to 0. Right? So once we have that, then what do we have? So star is going to be equal to, so as x goes to 0, that's just going to go to 0. So nothing exciting there because we have 0 minus 0 plus 0 minus 0 plus 0 minus 0 and so on, which you can show does converge to 0. So we just have the limit as x goes to infinity of the sum from k is equal to 0 to infinity of -1 to the power of k of x to the 2k plus 1 all over 2k plus 1 factorial times 2k plus 1. Right? So this is the thing for which we're taking the limit of. And you can approximate this limit by plugging in some arbitrarily large number for x and approximating it, but you can find that this is actually equal to pi over 2 exactly, right? But we're not going to prove that particular result because that's connected to that sine integral function, and there are some other key ways as well to prove this, which we're not going to get into here. So I hope you enjoyed these few examples on integral problems, and we'll see you in the next video. Take care.